Welcome dear students, and once again we are here in the classroom of number theory, and this is the third lecture on continued fractions. In the first two lectures we have defined continued fractions. We have seen how to convert a rational number into a simple finite continued fraction, and conversely we have had several theorems, several results based on continued fractions. And now in the previous lectures I also defined kth convergent, nth convergent, hi's and ki's, such that h naught is a naught, h1 is a naught a1 plus 1, hi is ai hi minus 1 plus hi minus 2, and similarly I have defined ki's such that every nth convergent cn can be expressed as hn divided by kn. And now we are going to proceed ahead. We are going to take some theorems based on these hi's and ki's, that means the two different sequences that define kth convergent. So let us see what the theorem says. Let hi's and ki's be the sequences defined as I have defined it in the previous video also, and I'm going to define it once again as h naught is equal to a naught, h1 is equal to a naught a1 plus 1, hi in general is ai hi minus 1 plus hi minus 2, k naught is 1, k1 is a1, and ki is ai ki minus 1 plus ki minus 2. In the previous video you have seen that if you define hi's and ki's like this, then cn, the nth convergent, is equal to hn divided by kn. But here we are going to prove some results on these hi's and ki's. Then show that two important results I'm going to prove here. The first one says that hi ki minus 1 minus hi minus 1 ki is minus 1 raised to the power I minus 1, and hi ki minus 2 minus hi minus 2 ki. This is the result where I and I minus 1, they are having a difference of 1, and here we are having a difference of 2 between I and I minus 2. In that case the result is equal to minus 1 raised to the power I into ai. These two results we are going to prove in this video. So let us see how to prove these results. I'm proving one by one, so I'm deleting the second one because I'm going to prove the first one, and we will prove both these results using the principles of mathematical induction. For I to be equal to 1, your left hand side is h1 k naught minus h naught k1. It is not h, it is h1. Your h1 is a naught a1 plus 1 into k naught. Your k naught is 1 minus h naught is a naught into k1. K1 is a1, and if you solve it you will get equal to 1, because this term will be cancelled out. You will get 1, or you can say minus 1 raised to the power 1 minus 1. That means minus 1 raised to the power I minus 1, because your I is 1. Your I is 1. So this one I have replaced by I. So this result is true for I is equal to 1. That is the first step of principles of mathematical induction. Now suppose that the result is true for I is equal to n. So if the result is true for I is equal to n, what you will get? You will get hn kn minus 1 minus hn minus 1 kn is equal to minus 1 raised to the power n minus 1. And let us see what happens if we take I to be equal to n plus 1? If the result is true for I is equal to n plus 1, the final step of the principles of mathematical induction will be over and the result will be proved. So let us see the case when I is equal to n plus 1. You substitute I to be n plus 1 here, you will get h n plus 1 kn minus h n k n plus 1. For this h n plus 1, use the definition of hi. You will get your hn plus 1 will become an plus 1 into hn minus hn minus 1, and this is multiplied by kn minus this is your hn, and for kn plus 1 apply the recurrence definition of ki. So kn plus 1 will become an plus 1 kn minus plus kn minus 1. Here also it is plus, not minus. And now open the brackets. Opening the bracket, the first term obtained will be an plus 1 hn kn, and in the second bracket the first term will be minus an plus 1 hn kn will be cancelled out. So this term will be cancelled out, and the two terms you are left with are hn minus 1 kn minus hn kn minus 1. You can take minus sign common, you will get hn kn minus 1 minus hn minus 1 kn, and from the induction's second step its value is equal to minus 1 raised to the power n minus 1, and there is a minus outside also, so it is minus n minus 1, or you can say minus 1 raised to the power n, or minus 1 raised to the power n, you can say n plus 1 minus 1. That means the result is true for I is equal to n plus 1 also. That means the result is true for all n because of the principles of mathematical induction. And now we are going to prove the second result on the same lines. The second result says that hi ki minus 2 minus hi minus 2 ki is equal to minus 1 raised to the power I into ai. Once again, let us move on to the first step of principles of mathematical induction. Put I is equal to 1. Substituting I is equal to 1 to the left hand side, you will get h1. Put I is equal to 2 because otherwise here it will be minus 1, which is not defined. So take I to be equal to 2. So h2 k naught minus h naught k2. For this h2, apply this result. So what is your h2? Your h2 is a2 h1 plus h naught into k naught is also there. This k naught minus h naught into k2. For k2, once again apply the recursion result. So k2 will become a2 k1 plus k naught, and now open the brackets. Opening the bracket, the second term in the first bracket is h naught k naught, and the second term in the second bracket is minus h naught k naught, so this will be cancelled out. And the two terms left are a2 h1 k naught minus a2 h naught k1. So a2 is also common. So a2 is also common. You will get h1 k naught minus h naught k1. And this h0 k1 minus h1 k naught minus h0 k1 is minus 1 raised to the power, this is minus 1 raised to the power 1 minus 1 because of the first part that we just have proved. So it is power 0. And your I is 2 here. Your I is 2 here. So what it is I minus 2. Minus 1 raised to the power I minus 2. Since I minus 2 and I are of the same parity. Same parity means they are either both odd or both even. So minus 1 raised to the power I minus 2 is also equal to minus 1 raised to the power I. because I and I minus 2 are having the same parity. So it is a2 minus 1 raised to the power I, and this 2 is also, you can replace it by I, because this is the case where you have taken I to be equal to 2. So the first step of the induction is being proved. That means the result is true for I is equal to 2. And now let us assume that the second step, let us assume that the result is true for I to be equal to n. If the result is true for I to be equal to n, that means your hn minus 2 minus hn minus 2 kn is equal to minus 1 raised to the power n an. This is true. This we have supposed that the result is true. And now we are moving on to the next step of principles of mathematical induction. That means when I is equal to n plus 1. For I to be equal to n plus 1, what your left hand side will be? It will be hn plus 1. This n will be replaced by n plus 1. K n minus 1, because n plus 1 minus 2 is n minus 1. Minus h n minus 1 k n plus 1. So this is the step now. And once again, what you have to do, you have to apply the recursion formula. For hn plus 1, from here you will get your hn plus 1 is an plus 1 hn plus hn minus 2 into kn minus 1, and similarly minus hn minus 1 into kn plus 1 is an plus 1 kn plus kn minus 1. And when you will open these brackets, the second term hn minus 2 kn minus 1, it is hn minus 1, not 2. It is hn minus 1. So the second step, hn minus 1 kn minus 1 minus hn minus 1 kn minus 1 will be cancelled. The second terms will be cancelled. An plus 1 is here, an plus 1 is here. So an plus 1 can be taken as common. What you will left with? Hn kn minus 1, hn kn minus 1, and minus hn minus 1 kn. And from the first part, what you have proved, this is equal to minus 1 raised to the power n minus 1. So you can write minus 1 raised to the power n plus 1 minus 2, n plus 1 minus 2. Moreover, n plus 1 minus 2 and n plus 1 are having the same parity. Either n plus 1 and n plus 1 minus 2 are both odd or are both even, and we are considering minus 1 raised to the power this, so this minus 2 can also be removed. So what you get? A n plus 1 minus 1 raised to the power n plus 1, that means minus 1 raised to the power I, a I minus 1 raised to the power I. So that means the result is also true for I to be equal to n plus 1, and that shows that by the principles of mathematical induction that the result is true for all natural numbers n. So we have proved very important two identities related to the two sequences defined as hn and kn. So these results may be used in the future questions, in the future lemmas, in the future theorem, but here we have just proved these two theorems. Now there is another very important question related to these HIs and KIs, and what this question says. Note down this question and we'll prove that if A naught, A1, A2, An, if this continued fraction is have Hn over Kn as nth convergent, Hn over Kn as nth convergent, then the reverse continued fraction an minus 1, an minus 2, and so on, a2, a1, a naught, this is equal to kn upon kn minus 1. So this is a very important, very easy question in fact also. So let us see how to prove it, how to solve it. So I'm starting from kn upon kn minus 1. Kn upon kn minus 1. For this kn, apply the recursion formula. So it will become an kn minus 1 plus kn minus 2 divided by kn minus 1. Now kn upon kn minus 1, an kn minus 1, and now separate these two terms. So separating an kn minus 1 upon kn minus 1 is equal to an plus the second term is kn minus 2 upon kn minus 1, and this kn minus 2 upon kn minus 1 you can write 1 upon kn minus 1 upon kn minus 2. Kn upon kn minus 1 is equal to this. Now in this identity you replace n by n minus 1. Replacing n by n minus 1, what you will get? You will get here kn minus 1 over kn minus 2 is equal to, here you will get an minus 1 plus 1 upon kn minus 2 upon kn minus 3. Then replace n by n minus 2, n minus 3 and so on. Continue this step. At some stage you will get k 2 upon k1 is equal to k2 upon k1 is equal to a2 plus 1 upon k1 upon k0. So it is equal to a0 plus 1 upon k1 upon k0. What is the value of k1? K1 is a1 and k0 is 1. So a1 divided by 1 is a1. So you will get a1 here. K1 is a1 and k0. Here it is a2, not a0. So these steps you will get. And now finally, let us see what is kn upon kn minus 1. So kn upon kn minus 1 is equal to, from the starting step it is an plus 1 upon this kn minus 2. But the value of kn minus 1 upon kn minus 2 from here, you can have an minus 1 plus 1 upon this. And once again in the second step you will get 1 upon an minus 2 plus 1 upon an minus 3 plus 1 upon and so on and so on. At last you will get plus a2 plus 1 upon a1. That means it is nothing but an minus 1, an minus 2 and so on up to a2, a1. So this is the reverse continued fraction of a0, a1, a2 and so on up to an. So this is an important question, and here we will try to shift on to the infinite continued fractions. But infinite continued fractions I will be taking in the next video. Till then, thank you once again.